All right, so today we are going to go ahead and do a little bit of review on designing for manufacturing and some tips and tricks that are going to help you guys out. Everybody should remember everything from DML. There's a bunch of great stuff on Mike's website. So I encourage anybody who's looking to go into more detail on DFM or get a full refresher, go on Mike's website, dig around a little bit, take a look at all of the stuff, and then just use this lecture as a little bit of pointers, tips and tricks, what have you. So the goal of designing for manufacturing, that is the first and foremost priority for us to discuss when going through this. There are two things that are goals. The first point is you want to minimize our manufacturing complexity. Right? We want to minimize our manufacturing complexity. We want to make our parts simpler, easier. Why? Things that are complex take longer to make. And we all know that time is equal to money. It is a fact of life at this point. All right, our second goal of DFM is to reduce the total number of parts that need to be manufactured. All right, so this makes sense. More parts are going to cost more money to manufacture. It's also going to take more time, and as we said, time is money. So we want to go ahead and minimize our total number of parts and our total manufacturing complexity. If you're paying attention to all of this, you will see the goal of DFM is just really at the end of the day to save money. That is what we are trying to do, is reduce how much money it is going to cost to make our parts, make our assembly, whatever it is that we are trying to do. So, moving on. Some general tips. Again, go back to DML. You can review all of these things. These are just my musings and discussion for you guys on this. So, tip number one is reduce the number of datums. All right, we're just trying to reduce the total number of datums on a part drawing. So there's this misconception that you need to have one drawing or one datum. You can have more than one. It is okay. You just need to justify it. You need a good reason for that. Common good reasons are hole spacings around shaft, proper alignment of a bolt pattern relative to itself for locating features. Things like this are all things that are good reasons. But you need to have that set. This is where everybody's favorite subject of tolerance loops come into play. All right, so this is where your tolerance loops come in. You can say, okay, cool, I need to reference this based off of a single datum. It is the way that things are going to work. It is what is going to help me make this part more accurately to the reason why I need these features constrained. Tip number 2 is to minimize your overall part size. Obviously, this comes with a disclaimer of minimizing part size within reason. You can't necessarily make a part so small that it doesn't fit in your assembly. You have to keep your overall sizes of everything in mind, but this is a part of it. Big reason here: small parts, use less material. Again, we're saving costs here. We're saving material. We're saving cost. That is the biggest priority. Tip number 3 is going to be use symmetry where you can. Again, this is where possible. We can't always use symmetry in everything we do, but we can try and use symmetry. All right, the point here is a left version and a right version is equal to 2 parts. All right, but if we have a symmetric version, it's only 1 part that needs to be made twice. It's fewer fixtures, fewer fixtures, fewer setups, whatever it may be. Tip number 4. Get stuff off the shelf when available. All right, you can typically find simple parts, bushings, spacers, etc., bearings. All right, these are all things that you can purchase very easily, but the warning here, get a nice big bold red warning. Avoid what I like to call OTS overflow. This is where you have so much of your assembly made out of OTS parts that your assembly is just this clunky mess of cobbled together whiz-bangs, doodads, and everything that you can buy on McMaster-Carr, rather than actually designing components. Design components to integrate with OTS parts where possible, but don't necessarily make everything out of 80/20 and McMaster-Carr parts, because your end result is not going to be a product. It is going to be a bunch of OTS parts that anybody could have put together. All right. So those are the general tips and tricks for the general tips and tricks for designing for manufacturing. Now let's talk tolerances. So talking tolerances, this should be super easy. Everybody should know this. Use large tolerances or larger tolerances where possible. All right, don't set everything to just be plus or minus 1/1000th of an inch. That's a U. Don't just set everything to be 1/1000th of an inch. If this is again, another one, you guys are gonna love this here. This is again where tolerance loops can help you out. Tolerance loops will go through and talk about, hey, this is, you can specify, it's easier for you to specify what your tolerances need to be with using tolerance loops and being able to come up with those. The next point on tolerances is use standard tolerances where possible. And we can actually take this pointer right here, and again, tolerance loops will help. The note here is if you calculate a tolerance that is larger, tolerance, if you calculate a tolerance that's larger than your standard, use the standard. That's the entire point of it. Your tolerance can be larger, but if you use a standard, it's easier for the machinist to do. It's easier for the drawer to make the part drawing. It's more consistent across everything. And you'll note that these 2 points seem to contradict each other. They don't contradict each other. They go hand in hand. If you calculate a plus or minus 1/16 of an inch tolerance, but you have a standard for plus or minus 50 thousandths of an inch, just go ahead and make it plus or minus 50 thousandths of an inch so it's uniform across all of your drawings. It makes it way simpler, way more straightforward. So easy things, easy pointers, very commonplace. Now let's talk about the things that we're going to need when we are actually machining parts. First big tip of the day here, through holes are easier and faster than blind holes. All right, just in case anybody is curious about what I'm talking about, if I have a block of material here, a through hole is a hole that will go all the way through it. A blind hole is one that would come down and only go to a depth of D instead of going all the way through my part as we have on the left. So that's the difference between how we would prefer to do things when it comes to drilling holes and making holes in parts. Next pointer, if you are using a blind hole, make sure that it has a comb bottom. Again, my typical disclaimer, if possible. And if possible means within the parameters of your design, not the parameters of your ability to CAD things. So if I have a blind hole in my part that looks like this, section view this to make it all appropriately drawn and all that jazz. This part right here versus this part here, we can see fairly straightforward that this hole on the left, what I'm going to do, the first thing I'm going to do is I'm going to come in and I'm going to drill it to that shape. And then I have to come in with a second step to cut out my corners. This is just a pain. It's extra setup. Again, it's extra time. And everything here that we are trying to do is to make this take less time. So we want to use cone bottom holes if we have a blind hole. But preface that with, you want to try and avoid blind holes where possible because they are harder to make in general. Making something to a specific depth requires more measurement, and it's just a little bit more complicated. A nice rule of thumb on hole depth. Nice rule of thumb for hole depth is that your length to diameter ratio should be less than 8:1. So our example here is you shouldn't take a 1/4 inch drill more than 2 inches deep and apart. You can, it's just bad practice, and it can cause problems down the road. You're more likely to break drill bits. You're more likely to have problems with your manufacturing when you go and do that. Other manufacturing tips here. Using standard sizes is incredibly helpful. You want to try and do this. So if we're in metric, metric uses whole number integers for end mills. That I end mills, and then it uses half steps for drills. Again, you can get other sizes in there. They're just less commonplace, and they're going anytime you do something less commonplace. It's a little bit more challenging to find, a little bit more expensive. For imperial, again, typically it's whole numbers. And then within those whole numbers, it's whole numbers and then 1/16 of an inch increments for end mills. Or I should say, instead of end mills, for general tooling, that is the case. For drill bits, you have 1/64 of an inch increments, actually. A little bit less common. Then you also have letter and wire gauge drills. So if you remember back to the drill indexes that there are in DML, you have the one rack that has everything in 1/64 of an inch from a 1/16 up to half an inch, and then you have the two other sides that have a lot more variability in tools and a lot more selection. And there's a lot of overlap with these drill bits for metric as well, or sometimes they are close enough to be well within your metric tolerance, so you don't always have to worry about it. But just keep those sizes in mind. Now let's talk material. Particularly material selection. All right, so if we're talking material selection, this is a huge thing. Material selection really, really, really matters here. If you've taken a look at the manufacturing processes chart um, or Excel spreadsheet, you have probably seen things like this. Oh, steel is 3 times harder to machine than aluminum. All right, so if you're making something out of steel, note that your material cost is going to be, it might be a little bit less than aluminum because aluminum tends to be slightly more expensive, but it is going to take 3 times longer um, to machine. Plus, you're also going to have increased tool wear due to heat. So your tools are going to wear out faster as well. So it's going to necessitate costing more money to make a part out of steel. Again, if you need the part to be made out of steel for whatever design principle, this is okay. But material selection needs to be well justified for why things are being made out of that. Stainless and stainless steels, rather. Stainless steels are 3 times harder than regular steel. Harder. So again, it's going to take longer. You're going to have increased tool wear. These guys also have to worry about work hardening occurring while machining them, particularly the 304 series and 316 series stainlesses. So with having work hardening happening, it's a whole host of other problems that come into play with our materials. The materials, titanium. Everybody loves titanium. It's the aerospace super metal. Titanium is on par with stainless. It's on par with our stainless steels. Just in general, polymers, the other end of the spectrum, tend to cut easier than aluminum. But we have one big issue with cutting polymers, and that is they can melt if you go too fast. So there is a thermal limitation on cutting polymers that tends to limit how quickly they can actually be cut. So that is our material selection. Again, the big note here, long eraser. The big note here, I will write up in just a second, is, and this is something that Mike covers very extensively in DML, actually put a star. Use the weakest material that meets your requirements. All right, use the softest material. It's just a good note to make that unless you need the extra strength of something like titanium or steel, or you need the corrosion resistance of stainless, make it out of a different material. That's going to be easier to cut. It's going to save you time. It's going to save you money, at least in the long run. Other note on material selection here, use raw material shapes. Raw material does come in a variety of different shapes. You all should have seen already. You should know, okay, cool. We can have our round, You probably have seen, square bar. You got our square bar. Um, I'm sure you all have seen L bracket shapes. I know that you've seen those in DML with all of the corner brackets. Uh, you've also got on the round bar side, you also have tubing. So there's no sense in drilling a hole through a cylindrical part if you can buy a piece of tube that has the correct diameter hole already through it, or a hole that's slightly smaller than your correct diameter, and you can just drill it out really quickly instead of having to step up through a variety of drill bit sizes. On the same part as square bar, you've got, C channel as an option here to buy instead of having to cut out the entire midsection of the bar. Buy C channel, and if it fits your material parameters and the sizes and shape you need, if you can tweak your design and modify your design slightly to work with it, why not go with C channel in the same veins as I-beam? You don't want to have to machine out the two flanges for an I-beam. It's going to waste a lot of time. A little bit less commonly known material shape is the lovely, that's a terrible line, the lovely hexagonal. So if you're making something where you need a custom designed bolt, or you need something that's going to go in, have some type of mechanical engagement with something, you can actually buy hex stock instead of having to machine all 6 flats on a piece of cylinder. The last thing you want to do is you do not want to take a piece of round and have to come in and machine away this little bit and that 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 little bit. Terrible hex, but you don't want to have to do that. You would just buy the hex instead. Buy hex stock. It solves that problem for you very easily. Again, simple thing when it comes to materials and material selection, just to get all that done. And that wraps up just general tips and tricks on designing for manufacturing and designing for manufacturability. And then we will also discuss designing for manual assembly, as well as some of the conflicting information that comes up in these designs.